This video is related with the book Statistical Modeling with R that I wrote and was published by Oxford University Press in 2023. In today's video, I'm going to fit a generalized linear mixed model if you're in the Frequentist framework, or a Bayesian hierarchical model if you're in the Bayesian framework, whose response variable is a proportion and that it uses a split plot experimental design. I will start again as usual with the exploratory data analysis, to be followed by the Frequentist model fitting and the Bayesian model fitting. The data and codes to run this analysis are shown in the can be found in the website shown in the screen. So the goal of this analysis is to assess the effect of several categorical explanatory variables on the proportion of above ground biomass of an invasive shrub. These categorical explanatory variables are the main crop, this being maize or soybean. The management, yes or no. This is related to the strength of the use of pesticides, and the competition from the main crop cover. This is a binary variable in which in some cases it was not removed the seedlings of the main crop when assessing the proportion of the biomass of this invasive shrub in Argentina. This experiment was carried out over 2 years that were contrasting in terms of their humidity, cold, wet and dry. So I started by importing the data set, and here is the response variable, the proportion of the above ground biomass, and the categorical explanatory variables. So I started by having a look at the structure of the data. Here I see how the blocks, there were 18 blocks, these were defined for each year or for different levels of the factor crop, the main crop. So there are 18 blocks, and this is the number of data points for each of these blocks. So then I further delved into the structure of the data set and realized that the authors defined 6 blocks for each crop in each year. So here are the 6 blocks for a given year wet in some of the crops. And within each block, the authors defined 2 large plots in which they applied the 2 levels of management, whether they applied or they did not apply herbicides. And in each large plot, they defined smaller subplots where they apply the 2 levels of crop level and they measure the response variable. These are the actual experimental unit of the variable of the experiment. So the experimental design is a split plot with randomized blocks. So the exploratory data analysis I explored the relation between the response and the exploratory variables. Here I show the box plot relating the proportion of above ground biomass for combinations of the variables crop cover, year and management for maize and for soybean. And by and large what we see is that if we take, just as an indication, the median of the different groups, the relationship between the medians depend on the different combinations of the levels of the categorical explanatory variables. So for fixed effects, I'm going to consider a model that has the 3-way interaction year, crop and management. This means that I'm going to include the single level effect of year, the single level effect of crop and the single level effect of management, all the pairwise interactions between year and crop, year and management, and crop cover and management, and the third order interaction. I'm also going to include the single effect of crop, and in random effects I'm going to include the following structure of random effects, random or population level effects, if you're in the Bayesian framework, in which we had a nested hierarchy of crop cover nested within management, nested within blocks. So the Frequentist model fitting, the statistical model, the response variable has a beta distribution. At the end show it, but it sees this being a proportion, the most natural probability distribution to model the variability of this response variable is a beta distribution whose parameters are the mean and a dispersion parameter that governs the relationship between the mean and the variance of this probability distribution. In terms of the link function is going to be logit, so the logit of the mean. Here I'm going to have the single level effect of crop and the third and the first order pairwise interactions and third order interactions of these three factors, plus the random effects, blocks, plots within blocks, subplots within plots, and all these coefficients B are going to be modeled as if having a normal distribution and a given variances that are going to be different for each of these three nested random effects. So the effects of the population level, the effects of the fixed effects and those of the random effects are going to be additive in the space or scale of the link function, logit in this case. So here is the fitted model, fitted with the package GLMM TMB, and here's the summary of the model that has two main parts. The random effects, in which we have the variances or standard deviation, as you prefer, for the blocks, the management units within blocks, the crop within management within blocks. And here we also have the intercept, which is the logit of the mean of the response variable for the reference level of each of the four explanatory variables: crop, year, crop cover, and management. So these are the single level effects. These are the pairwise interactions, and here's the third order interaction. Here we have the estimates, the standard error, and the p-values. I'm not going to focus on the statistical significance of each of the term, but rather I prefer to show how to obtain and interpret the parameters of the fixed level effects by having a closer look at these three third order interactions in the next slide. So the fixed effects, here are the coefficients, the same that I showed in the previous slide. And so here we have the three, we have a cube. Here we have manage, and for the combinations of levels of the three explanatory variables, here is management, here is year, white and red, wet and dry, and here is crop cover. So here we have in the vertices of each of this cube, we have the combinations of levels of each of the explanatory variables. So I'm going to show how to actually obtain the predicted mean for each of these combinations of levels of all these explanatory variables that have single effects, pairwise interactions, and third order interactions. So the first order effects, here is the reference level for the three explanatory variables, categorical explanatory variables. Here is the 0.89. This value minus 0.89 appears in all vertices of this plot, and here I'm simply adding, while keeping the management no, which is the reference level. Then I'm going to management yes, which is the other level. I'm going to add 0.25, which appears somewhere in this slide. So in the same way, I just add the effects of all the pairwise, all the single level effects of all the explanatory variables, and after adding these terms, which are the values of the logit of the mean of the response variable after including just the first order effect, I'm going to add the second order interactions by putting the specific coefficients that need to be added in each case. So here are again the coefficients of the fixed effects for this model. I recall yet again all the combinations of levels of the three factors: year, management, and crop cover. And so after adding the interactions, I'm going to add the third order interaction in the top right hand corner at the back. And then after adding these values, now these values, I recall, these are the logit of the mean of the response variable. I show the predicted means of the response variable after inverting the link function. So here are the predicted means of the proportion of the above-ground biomass for each of the combinations of the levels of the three explanatory variables. We can also obtain the random effects. These random effects can be shown in plots. Here we have for the blocks, the 18 blocks ordered in ascending order. Here we have the blocks within the plots within the blocks, and here we have the subplots and the combination, the three-way combinations of subplot, plot, and blocks, again in ascending order. This bar here shows the standard error for these estimated coefficients. So we see that, for instance, just to take one example, some of the blocks are a negative coefficient, meaning that the predicted logit of the mean of the response variable is smaller than the one predicted by the fixed effects, and for some other blocks is slightly higher. And likewise, we can make the same interpretation for the other two components of the random effects. So in order to assess the goodness of fit of the model to the data, we use the package Mixed. This package is needed to take the input of packages of models fitted with the package GLMM TMB. So I obtain the basic input of this the residuals. Then I simulate the Donald-Smith residuals using the package Dharma. These simulated residuals are converted to a normal distribution. I recall again that these residuals will only have a normal distribution if the model fits well, and then I use a function that I wrote, Cook distance GLMTMB, that allows us to obtain the Cook distances for each of the points for a model obtained with the package GLMM-TMB. This function can also be found in the codes that are provided as indicated in the first and the last slide of this video. So the plots resulting from this analysis, we have a series of plots. First of all, the plot of the residuals against the fitted value is sort of acceptable. There is a slightly upward trend, which is not extremely good, but this is not too bad. We see that the variation is slightly smaller here in the left and in the right hand side of the plot. When we compare for the different combinations of crop cover and year, the residuals for the different combinations of crop cover and year and crop and management, what we see is that the medians are all very close to zero, and that the variance as estimated, or the variability as indicated by the width of the box, is not too dissimilar for each of the four groups shown here. We have the Cook distances. We have a few data points that are seem to have a very large Cook distances. It would be wise to check whether the influence of these 4 points, for instance, by deleting them from the model and refitting the model to see if it makes any qualitative important difference on the fitted parameters. The residuals, the transformed Donald-Smith residuals, by and large, with the exception of a few data points in the lower tail, by and large follow a normal distribution. And likewise, the three components of the random effects, they also seem to have a normal distribution. So by and large, while it's not excellent, this model seems to have fitted pretty well the available data. The main results can be communicated using the conditional curves. These conditional curves show us the predicted relationships, the relationship predicted between the explanatory and the response variable predicted by the model. Here we have for the 2 years wet and dry, for no management and for yes management, for the different crops. So we have the predicted values of these of the different means and confidence interval predicted by the model and the actual data. We see, of course, that the data has much larger variability than the conditional curves are shown here, as shown by the conditional curves. In terms of the Bayesian model fitting, the statistical model is of course the same. The response variable follows a beta distribution with a given mean and a dispersion parameter, and the logit of the mean is modeled as a function of the categorical explanatory variables, including 3 of them in pairwise and triple interactions, and the group level effects for each of the components, where each of these group level effects is modeled as if having a normal distribution with a given mean and a given variance that is different for each of the components. We enter the formula here as a shorthand, and we use the command get prior of the package BRMS in order to obtain the priors that need to be defined for all the components of the model. Here are the population level effects, and here are the components of the priors for the group level effects. All these priors are defined in the logit scale. I simply define one prior for all coefficients of type B. I use the logit as a way of the logit function as a way of defining the variance of these coefficients. So please have a look in the book for further explanation as to why these priors were set. Then I run the model. I fitted the model m4.brms with the fix and with the population level and group level effects, with the priors that I just defined. Beta and the rest of the components were discussed in previous videos and need not be repeated here. So the summary of the model contains what here is called the multi-level hyperparameters, or population or group level parameters. Here we have from bottom to top the standard deviation from top to bottom of the blocks, the management within the blocks, the crop cover within management within blocks. Here we have the standard deviations. Here we have the standard errors, or the standard error, which amounts to the standard deviation of this marginal posterior distribution and the 95% credible intervals. This is for the group level effects. For the population level effects, we have again the coefficient. We have here the means, standard deviation, and 95% credible interval for all these coefficients. For the interpretation of these coefficients, I recall that this can be done with the same approach followed for the Frequentist model, and for the sake of brevity, I'm not going to repeat them. We also have the phi parameter, the dispersion parameter of the beta distribution, estimated whose mean is estimated to be this value of 27.32, and here is a 95% credible interval. What we see here is that the R-hat statistics are all pretty high and close to 1, as sign that the three chains of the model have converged to a common posterior stationary distribution, and the effective sample sizes of each of the parameters suggest that we have very many statistically independent estimates for each of these parameters for both the population level parameters and for the group level parameters. Of course, all these parameters are estimated in the logit link scale, as it is always the case for this type of models, and more generally speaking in the link scale for any GLM type of model. So we can have a look at the posterior distributions of the main parameters, of the population level parameters, and we do see indeed that the three chains have converged to a common posterior distribution. The percentage of variation explained by the model is relatively small. It's about 28%, with a credible interval between 23 and 34%. This is using the metric devised by GLMM et al. In a paper in 2018. So we can also have a look at the autocorrelations of the parameters having population level effects. This is for each of the chains, and we see that by and large, with the exception of some parameters for certain chains, and these also have an autocorrelation of 0.1 or 0.2, which is pretty moderate. Our estimates seem to be the estimates of the parameters for each of the chains seem to be by and large statistically independent. That is, they provide statistically independent information for the computation of the summary statistics of these marginal posterior distributions. So we can also assess the goodness of fit of the model to the data using the Donut-Smith residuals obtained using the package Dharma by using the posterior predictive distribution. Here is the posterior predictive distribution that is stored here, and with this posterior predictive distribution we use the command create Dharma to obtain, when this posterior predictive distribution, the residuals. These residuals are transformed, these Donut-Smith residuals are transformed to have a normal distribution and stored, and then we create a data frame with all the input necessary for the plots of the residual analysis. They include the explanatory variables, they include the fitted values, the mean of the fitted values, and they include the Pareto K coefficients that will allow us to ascertain the importance of each data point on the posterior distributions obtained by the model. The final plots are shown in this slide, and here we have the plot of the residuals against the fitted values. By and large, this is a random fit. We don't see any trend whatsoever here in this plot A, and in plots B and C, for different combinations of crop cover and year management and main crop, what we see is that the median of the residuals are all very close to zero, and the variability, as indicated by the width of the boxes, are all pretty similar, if not nearly identical. We see that the transformed Donut-Smith residuals do indeed have a normal distribution, as indicated, that would suggest a good fitting model. The Pareto K coefficients suggest that we have 1, 2, 3, 4, 5 points in just the OK range and 1 in the bad range, but all the rest of the points are pretty good. Pretty good in the sense that they did not have an important influence on the posterior distribution of this fitted model. What we could do is perhaps remove these 4 or 5 points and see if there are qualitative difference between the two fits of the model, the one with all the data and the one without these 4 or 5 points, to see if there are any qualitative difference in the main summary statistics of the posterior distributions. In terms of evaluating whether the different components of the group level effects have a normal distribution, we do see indeed that 2 of the 3 are pretty good. That is, they do have a normal distribution, but one of them has 3 points that are pretty well off the line of perfect fit. Again, we could examine the influence of these of all the data from each of these associated with each of these 3 points by fitting the model without them, and seeing if there is any important qualitative difference between the two fits of the same model. So again, we can obtain, as usual, the conditional curves here shown for management no and management yes, for the different combinations of the main crop and the 2 years. And here are the predicted values, and the dots indicate, the shaded dots indicate the distribution of the data. We can obtain also the posterior distributions of the population level effects, here shown in the mean and the 50% credible interval, and this is the 95% credible interval. These are true probability distributions for each of the model parameters having population level effects. And in Bayesian models, we also obtain posterior distribution for the group level effects. Here they are. For each of them, we have a posterior distribution. This is a true probability distribution for each of these posterior for each of these group level effects. The blocks, the plots within blocks, the subplots within plots within blocks. So in this video I have shown how to fit a generalized linear mixed model of proportions with data that came from a split plot experimental design, starting with an exploratory data analysis, and was followed by the Frequentist model fitting and the Bayesian model fitting. I hope you found this video interesting, and here are the location where you can find the data and the codes to run this analysis. Thank you very much for your attention.